Every force in the universe is written in a mathematical language that was invented by a 20-year-old prisoner the night before he was shot to death in a duel. He submitted the work 3 times. It was rejected 3 times. The foundation of modern physics sat in a drawer for 14 years. You think of abstract algebra as something that belongs to chalkboards and graduate seminars, settled, institutional. But group theory was not born in a university. It was born in a letter, written by candlelight, by a boy who knew he would be dead by morning. And the standard model of particle physics, the most precisely tested theory in the history of science, cannot be stated without the framework he created. Remove it, and the equations governing every particle in your body stop working. Tonight, I want to walk you through May 29th, 1832, through 3 rejected manuscripts, a dead referee, Emmy Noether barred from presenting her own theorem, all the way to a bubble chamber at Brookhaven in 1964, where a particle appeared exactly where a dead boy's algebra said it would. Get comfortable. This one runs deep. If you're not subscribed, join up. If you want more across physics, math, and history, there's a Patreon where that happens on a broader scale. Stay until the end, because the question you walked in with is about to be replaced by a much stranger one. Let's go back to where this began. On the 11th of February 1964, a particle appeared inside a bubble chamber at Brookhaven National Laboratory on Long Island, New York. It left a track that curved exactly the way the mathematics said it would curve. It had a mass of 1672 megaelectron volts, a charge of -1, and a strangeness of -3. It existed for less than a 10 billionth of a second, and the mathematics that predicted it, down to within 1% of its mass, had been scrawled in the margins of a rejected manuscript by a 20-year-old who had been dead for 132 years. His name was Évariste Galois. He was shot in the stomach at 25 paces on the morning of May 30th, 1832, outside a boarding house near the Étang de la Glacière in Paris. He died the following day at 10 in the morning at Hôpital Cauchy of acute peritonitis in his younger brother Alfred's arms. His last words were, "Do not cry, Alfred. I need all my courage to die at 20. The night before the duel, knowing he would likely not survive, he sat down and wrote a letter to his friend, Auguste Chevalier. 7 pages, crammed with mathematics. In the margins where the proofs were incomplete, he wrote over and over, "I have not time. I have not time." He used the old French spelling, "Je n'ai pas le temps," as if even the letters were being rationed. That letter, and the manuscripts attached to it, contained the seeds of what is now called group theory. And group theory is not some obscure branch of abstract algebra that only mathematicians care about. Group theory is the language in which the physical universe is written. Every symmetry in nature, every conservation law, every classification of every subatomic particle, every force that holds matter together and every force that tears it apart is expressed in the mathematical framework that a dying boy put on paper because he ran out of days to publish it properly. The standard model of particle physics, the single most precisely confirmed theory in the history of science, is built on the gauge group SU3 times SU2 times U1. 3 symmetry groups, 3 forces, every particle you have ever heard of, every electron, every quark, every neutrino, every photon, is classified by its representation under these groups. And the mathematical concept of a group, the concept that makes the entire structure possible, was formalized for the first time by Évariste Galois in a prison cell at the age of 19, after being rejected by every mathematical institution in France. I spent an unreasonable amount of time trying to understand how this story is possible. Not the biography. The biography is well documented. What I could not understand is the gap between the size of what Galois discovered and the complete systematic failure of every person and institution around him to see it. Because Galois did not submit his work once and get rejected by a careless reviewer. He submitted it 3 times to 3 different gatekeepers of French mathematics over a period of 2 years. The first referee advised him to rewrite it. The second died with the manuscript on his desk. The third read it carefully and wrote that the reasoning was, and I am quoting the actual report, preserved in the Academy's official records, neither sufficiently clear nor sufficiently developed for us to judge its rigor. That third referee was Simeon Denis Poisson, one of the finest mathematicians in France. And what Poisson was looking at and failing to see was the foundation of modern algebra and the future language of all of physics. And the question that this entire story comes down to, the question I kept returning to and could not shake loose, is not why Galois died young. Brilliant people die young all the time, and it is always tragic, and it is never the interesting part. The question is, what does it mean that the mathematical structure governing the physical universe was visible to a teenage prisoner in 1831, a full century before physicists even knew they needed it? What does it mean that the language of reality was written before anyone knew what reality was made of? That question does not have a comfortable answer, and I am going to follow it all the way down. Bourg-la-Reine, 1811, a small town just south of Paris, on the road to Sceaux. Évariste Galois was born on October 25th to Nicolas Gabriel Galois and Adelaide Marie de Mante. His father was the mayor, a man of the liberal Enlightenment tradition, educated, politically engaged, the kind of person who wrote satirical poems for local entertainment and ran a boarding school where young men of the town received their education. His mother was the daughter of a jurist, and she had received a rigorous classical education that was unusual for women of her generation. She spoke Latin, she had read the classical philosophers, and she taught Évariste at home until the age of 12. No mathematics. That is important. For the first 12 years of his life, the person who would create the most consequential mathematical framework in history received no mathematical training whatsoever. His education was literature, languages, history, philosophy. When he entered the Lycée Louis le Grand in Paris in October of 1823, at the age of 11, he had no particular mathematical background and no particular mathematical reputation. Louis le Grand was the most prestigious secondary school in France. Its alumni included Voltaire, Robespierre, and Victor Hugo. It was rigorous, hierarchical, and deeply conservative in its pedagogy. And for the first 2 years, Galois was a thoroughly unremarkable student. His marks were mediocre. He repeated the seconde, the equivalent of a year being held back. His teachers noted nothing exceptional. And then, in 1826, at the age of 14, he entered the mathematics class taught by Hippolyte Jean Vernier. And something happened. The accounts from this period describe it almost like a conversion experience. Within weeks, Galois had obtained a copy of Adrien-Marie Legendre's Éléments de Géométrie and read the entire thing cover to cover. His classmates later recalled that he read it the way other students read novels, in a few sittings, absorbing theorems the way you absorb plot. Then he moved to Joseph Louis Lagrange, not introductions to Lagrange, not textbooks about Lagrange's methods. The primary sources, Lagrange's own reflections sur la résolution algébrique des équations, published in 1717 and 1701. Lagrange's resolution des équations numériques. These are dense, technically demanding works written by one of the most formidable algebraists of the 18th century. Galois consumed them at 14. His mathematics teacher, Louis-Paul-Émile Richard, recognized what was happening. Richard was not a famous mathematician, but he was a gifted teacher with an eye for talent. And he later said that Galois should have been admitted to the École Polytechnique without examination, that requiring him to sit for the entrance exam was an insult to his obvious abilities. Richard saw genius. The institution did not. And I want you to picture what this looked like from the inside, because the popular image of a mathematical prodigy is someone who can do arithmetic quickly or solve problems that other students find difficult. That is not what happened with Galois. What happened was more radical. Galois did not learn existing mathematics faster than his peers. He began creating new mathematics almost immediately. His first original research dates to his last year at Louis-le-Grand. At the age of 17, before he had received any university-level instruction, he was producing results in the theory of continued fractions and in the theory of equations that were publishable in professional journals. His first paper appeared in March of 1829. He was 17 years old, and within months he was working on the problem that had defeated 3 centuries of professional mathematicians. Try to imagine what it must have been like to be his classmates, or his teacher, or the examiners who could not follow his reasoning at the Polytechnique. You are in a room with a boy who has been studying mathematics formally for 2 years and who is already working at the frontier of the subject, producing ideas that the most powerful mathematicians in France will struggle to understand for decades. The gap between Galois and his surroundings was not a matter of degree, it was a gap of kind. He was not just better at the existing mathematics. He was thinking in a different mathematics, one that had not been built yet, one that he was building in real time, and the people around him were evaluating him using the tools of the mathematics he had already surpassed. Because in 1828, at the age of 16, Galois took the Polytechnique entrance examination for the first time, and he failed. The École Polytechnique was the pinnacle of French technical education. Founded during the Revolution, it had trained the great mathematicians and engineers of the Napoleonic era. Admission was by competitive examination, and the examiners were rigorous, formal, and unforgiving. Galois, who had been teaching himself from primary sources for 2 years and had already begun producing original research, was expected to present his work in the structured, step-by-step manner the examiners demanded. He could not, or would not. His mind moved too quickly, made connections the examiners could not follow, skipped steps that seemed obvious to him and incomprehensible to them. He failed. The following year, 1829, he tried again. And the story of the second Polytechnique examination has become one of the most retold anecdotes in the history of mathematics. Though I should tell you that the most dramatic version cannot be independently verified. The tradition says that Galois, frustrated beyond endurance by an examiner named Dinet, who could not follow his reasoning, picked up an eraser and threw it at the examiner's head. Whether that specific detail is true or not, the outcome is documented. He failed again, permanently. The Polytechnique, the institution where he belonged, the institution where his mathematical peers would have understood him, was closed to him forever. And between those 2 failures, the event that cracked his life open, on July 2nd, 1829, Évariste's father, Nicolas Gabriel, committed suicide. The circumstances are documented and ugly. The local parish priest in Bourg-la-Reine, a man named Gras, or Grab, depending on the source, had been engaged in a political feud with Nicolas Gabriel over control of the town's administration. The priest forged a series of obscene poems and distributed them under Nicolas Gabriel's name, a deliberate campaign to destroy his reputation in the community he had served as mayor. Nicolas Gabriel, unable to clear his name, traveled to Paris and hanged himself. He was 54 years old. Évariste was 17 when they buried his father. And the effect was detonation. I am telling you this in detail not because biography is the point of this story, but because the personal and the mathematical are not separable here. They never were. A boy watched the local representative of institutional authority systematically destroy his father through slander and forgery. That father was dead within months, and that same boy, within the next 2 years, submitted his most important mathematical work to the most powerful institutional authorities in French science and watched them ignore it, lose it, and reject it. The pattern was identical. The institution could not see what was in front of it, and the person who had something real was ground to dust. By December of 1829, Galois had at least been admitted somewhere. The École Normale Supérieure, then called the École Préparatoire, was a step below the Polytechnique in prestige, focused on training secondary school teachers rather than engineers and scientists. His examiner noted on December 29, 1829, "This pupil is sometimes obscure in expressing his ideas, but he is intelligent and shows a remarkable spirit of research. Sometimes obscure in expressing his ideas." Remember that phrase. It is going to echo through the next 2 years with increasing volume. Galois entered the École Normale, but his mathematical work had already begun, and it was already running ahead of the institution's ability to evaluate it. His first published paper appeared on March 1, 1829, in the Analyse des Gell-Mann, a demonstration of a theorem on periodic continued fractions. Technical, competent, not yet the work that would change mathematics, but it was the beginning. By May of 1829, at the age of 17, he had submitted 2 papers to the French Academy of Sciences through Augustin Louis Cauchy. This is where the institutional catastrophe begins. And I want to be precise about what happened with Cauchy, because the popular version is wrong, and the real version is, in its own way, worse. Augustin Louis Cauchy was born in 1789, the year of the Revolution, and by 1829 he was one of the most prolific and powerful mathematicians in Europe. He was also a devout Catholic, an ultra-royalist who had followed Charles X into exile after the July Revolution, and a man whose political views were diametrically opposed to the liberal tradition that had produced Galois' family. Cauchy was brilliant, politically conservative, and institutionally dominant. He controlled access to the Academy's proceedings. Now, the version of this story that you have probably read, the version that E.T. Bell popularized in his 1937 book Men of Mathematics, is that Cauchy carelessly lost Galois' manuscripts. That is not what happened. The historian René Tarton published a meticulous archival study in the Revue d'Histoire des Sciences in 1971, volume 24, number 2, titled Sur les relations scientifiques d'Augustin Cauchy et d'Évariste Galois. What Tarton found, working from the Academy's session records and Cauchy's correspondence, is that Cauchy did not lose the papers. Cauchy was scheduled to present a report on Galois' 2 manuscripts at the Academy session of January 18th, 1830. The report never happened because Cauchy instead advised Galois to withdraw the 2 separate papers, revise them, combine them into a single stronger manuscript, and submit that combined work for the Academy's Grand Prize in Mathematics. It was not negligence. It was advice. Whether it was good advice is another question, because it sent the manuscript down a path that ended at a dead man's desk. Galois following Cauchy's recommendation, withdrew the papers and spent the next month preparing a single, comprehensive memoir. In February of 1830, he submitted it for the grand prize. The manuscript was sent to Joseph Fourier. Fourier, born in 1768, the man who had invented Fourier's series, the decomposition of functions into sums of sines and cosines, one of the most powerful tools in all of applied mathematics. He had served Napoleon as prefect of the Department of Isère. He had accompanied the Egyptian expedition. By 1830, he was the perpetual secretary of the Academy of Sciences, one of the most powerful positions in French science, and he was 62 years old, and his heart was failing. On May 4th, 1830, Fourier fell while descending a staircase and severely aggravated a pre-existing cardiac condition. 12 days later, on May 16, 1830, Joseph Fourier died of a cardiac aneurysm at his home in Paris, and Galois' manuscript, the revised combined memoir that Cauchy had told him to prepare, the one that contained the seeds of modern algebra, was on Fourier's desk, or in Fourier's papers, or somewhere in the chaos of a dead man's estate. It was never found. The manuscript disappeared, not rejected, not critiqued, not even acknowledged as received, simply gone, lost to an aneurysm and a staircase, and the institutional entropy that follows when a powerful man dies and nobody knows where he kept his papers. The 1830 Grand Prize in Mathematics went jointly to two recipients. One was Carl Gustav Jacob Jacobi, the great German mathematician, for his work on elliptic functions. The other was Niels Henrik Abel. Posthumously, Abel, I need you to hold his story alongside Galois's, because the parallel is almost too precise to be real. Niels Henrik Abel, born August 5, 1802, in Finnøy, Norway. Like Galois, a prodigy who outstripped his teachers before the age of 20. Like Galois, a man who made a foundational contribution to the theory of equations. Like Galois, a man who submitted his work to the French Academy of Sciences. Like Galois, a man who was ignored. In 1824, at the age of 22, Abel proved that the general Quintic equation, the polynomial of degree 5, cannot be solved by radicals. There is no formula analogous to the quadratic formula that works for all fifth-degree polynomials. He published this result in a 6-page pamphlet self-published in Christiania, Norway. Because he could not afford journal fees, he sent copies to the leading mathematicians of Europe. Cauchy, who received the copy, apparently never read it. Gauss, who received the copy, set it aside and later said he did not have time for it, though some historians believe he never even opened the envelope. Abel expanded the proof and published it in August Leopold Krell's journal, Für die reine und angewandte Mathematik, Volume 1, in 1826. It remains one of the most important papers in the history of algebra. He then travelled to Paris, the centre of the mathematical world, hoping for recognition and a position. He submitted a major memoir on elliptic functions to the Academy. Cauchy was appointed referee. Cauchy mislaid the manuscript for months. Legendre and Cauchy eventually reviewed it, but by then, Abel had returned to Norway, penniless and ill. On April 6, 1829, Niels Henrik Abel died of tuberculosis at Froland, Norway. He was 26. He had been ill for months, coughing blood through the winter, too poor to afford proper medical care, too far from the centres of mathematical power to benefit from the reputation his work was slowly building. 2 days after his death, a letter arrived from August Leopold Krell offering him a permanent position as a professor in Berlin. Krell had been lobbying for the appointment for years. The letter arrived at Froland. Abel's family opened it. Abel never saw it. He was already in the ground. 2 days. The distance between vindication and death was 2 days, and the vindication itself had come not from the French Academy, which had lost and ignored his work, but from a German editor who had recognized Abel's genius when the establishment could not be bothered to read his papers. 2 young men, both brilliant, both working on the theory of equations, both submitting to the French Academy, both destroyed by the same institution's failure to read what was in front of it. Abel dead at 26 of tuberculosis. Galois dead 3 years later at 20 of a gunshot wound. The Academy gave Abel a posthumous prize and gave Galois a rejection letter. And the mathematical tradition that grew from their combined work, the theory of polynomial solvability, the theory of groups, the theory of fields, the entire edifice of abstract algebra would eventually become the most important mathematical framework in all of physics. But in 1830, with Abel dead and Galois' manuscript lost on a dead man's desk, none of that existed. The mathematics was written, the mathematics was correct, and nobody could be bothered to read it. There was still one more chance. In January of 1831, at the personal invitation of Simeon Denis Poisson, Galois submitted a new and hopefully final version of his work, the premier mémoire. Mémoire sur les conditions de résolubilité des équations par radicaux. The memoir on the conditions of solvability of equations by radicals. This is the paper that contains the theorem, the paper that defines the Galois group, proves the solvability criterion, and opens the door to all of abstract algebra and everything that followed from it. Poisson was born in 1781. He was a formidable mathematician, known primarily for his work in mathematical physics. The Poisson equation, the Poisson distribution, Poisson's ratio. He was methodical, careful, and thorough. He was not a man who would casually dismiss a paper. He and his co-referee, Sylvestre François Lacroix, spent nearly 6 months reviewing Galois' submission. The rejection came on July 4th, 1831. The report is preserved in the Procès-verbaux des séances de l'Académie des Sciences, Volume 9, pages 660 to 661. The exact words which I have verified against the original French. Nous avons fait tous nos efforts pour comprendre la démonstration de M. Galois. Ces raisonnements ne sont ni assez clairs, ni assez développés pour que nous ayons pu juger de leur exactitude, et nous ne sommes pas en mesure d'en donner une idée dans ce rapport. On devrait alors attendre que l'auteur ait publié en entier son travail pour se former une opinion définitive. We have made every effort to understand Monsieur Galois' proof. His reasoning is neither sufficiently clear nor sufficiently developed for us to judge its rigor, and we are unable even to give an idea of it in this report. One should wait for the author to publish his work in its entirety in order to form a definitive opinion, neither sufficiently clear nor sufficiently developed. That is what Simeon Denis Poisson wrote about the paper that would become the foundation of abstract algebra, the framework that would eventually express the fundamental forces of nature, the mathematical language without which the standard model of particle physics cannot even be stated. It is not clear enough. We cannot judge it. We recommend waiting. They recommended waiting for a 20-year-old political prisoner who would be dead within 11 months. And the reason Poisson could not understand it was not that the paper was badly written, though it was certainly terse and compressed. It was that Galois was working inside a mathematical universe that did not yet exist in anyone else's mind. He had invented the concept of a group, the concept of a normal subgroup, the concept of a solvable group, the concept of what we now call a field extension and the correspondence between field extensions and group structures, all in a single paper, all at once, using terminology he had to create from scratch because the words did not exist in any language. He was writing mathematics that required a conceptual vocabulary nobody else possessed. Poisson was one of the best mathematicians in France, and he could not follow the argument because the argument was in a language that had one speaker. That report reached Galois in prison because by July of 1831, Évariste Galois was an inmate at Sainte-Pélagie. The politics had moved fast. You need to understand the context because it is not separable from the mathematics. France in 1830 was a pressure cooker. Charles X, who had succeeded his brother Louis XVIII in 1824, had been tightening the screws of reactionary governance for 6 years. In July of 1830, he issued the 4 ordinances, suspending freedom of the press, dissolving the newly elected Chamber of Deputies, restricting the franchise, and ordering new elections under rigged rules. The response was immediate. On July 27th, 28th, and 29th, the people of Paris fought in the streets. The Trois Glorieuses, barricades in the faubourgs, musket fire in the Rue Saint-Honoré, the tricolour raised over Notre Dame, and the students of the École Polytechnique, the institution that had rejected Galois, were in the thick of it. They manned the barricades. They fought alongside the workers and the artisans. They were celebrated as heroes of the revolution. The Polytechnique became a symbol of youth, courage, and republican virtue. But the students of the École Normale, where Galois was enrolled, were locked inside. Their director, Joseph Daniel Guignot, bolted the gates and posted guards and forbade any student from joining the fighting. Galois was locked inside while his peers at the Polytechnique fought for the republic he believed in. Think about the rage. The Polytechnique, the school that had rejected him twice, was on the barricades. Its students were heroes. And Galois, who had more reason than any of them to fight, who had watched institutional authority destroy his father, who was already radicalized by the Academy's treatment of his work, was locked behind bolted gates by a director who valued order over justice. The revolution succeeded. Charles X abdicated. But instead of the republic the revolutionaries had fought for, the liberal monarchy of Louis-Philippe d'Orléans was installed. The bankers and the moderate liberals cut a deal. The king was replaced with a different king. For the workers and students who had bled on the barricades, it was a hijacking. For Galois, it was a double betrayal. The École Normale had prevented him from fighting, and the revolution itself had been stolen, its promise of a republic replaced with another monarchy wearing liberal clothes. In December of 1830, Galois published a letter in the Gazette des Écoles, attacking Guignol by name for locking the students inside during the revolution. He was expelled. The expulsion was officially confirmed on January 4th, 1831. The same month he submitted his final memoir to Poisson. Free of the institution, Galois threw himself into radical republican politics with the same intensity he brought to mathematics. He joined the Société des Amis du Peuple on November 10th, 1830, the most militant of the republican societies, alongside men like François Vincent Raspail and Louis Auguste Blanqui. He attended meetings, he made speeches, he drilled with weapons. And on May 9th, 1831, at a public banquet at the restaurant Aux Vendanges de Bourgogne, celebrating the acquittal of 19 Republican artillery officers, Galois made the gesture that would cost him his freedom. 200 people were at the banquet. Alexandre Dumas, the novelist, was among them, and later described the scene in his memoirs. Galois rose, raised his glass, and said to Louis Philippe. As he said the name, he held a knife above the cup. The meaning was unmistakable. In the charged political atmosphere of 1831 Paris, it was a public death threat against the king. Dumas wrote that half the room erupted in cheering and half fled through the windows. Galois was arrested the next morning, May 10th, at his mother's house in the Rue des Bernardins. At his trial on June 15th, the defense argued that what Galois had actually said was, to Louis Philippe if he betrays, and that the conditional clause had been drowned out by the noise. Whether this is true or a legal fiction is impossible to determine. The jury acquitted him. He was free for exactly 1 month. On July 14th, 1831, Bastille Day, Galois was at the head of a Republican demonstration marching across the Pont Neuf. He was wearing the uniform of the disbanded Republican artillery, which was now illegal. He was carrying a loaded carbine, several pistols, and a dagger. He was arrested on the spot. The charge was illegal wearing of a military uniform. The sentence, delivered on October 23rd, 1831, was 6 months in Sainte-Pélagie prison. Sainte-Pélagie was a political prison, and the political prisoners were housed in a separate wing from the common criminals, but conditions were still harsh. Raspail, who was incarcerated alongside Galois, kept a journal, and on July 25th, 1831, Raspail recorded something that Galois said while drunk. The words, which Raspail wrote down, "And I tell you, I will die in a duel on the occasion of some worthless woman of the lowest sort. Why? Because she will invite me to avenge her honor, which another has compromised." Think about that. 10 months before the duel, drunk in a prison cell, Galois predicted his own death. Not the mathematics, not the physics, the death, as if he could see the shape of his life from the inside and knew how it ended. By March of 1832, the cholera epidemic that had been devastating Paris, killing thousands, had reached the prisons. On March 16th, Galois and several other prisoners deemed at risk were transferred from Sainte-Pélagie to a kind of halfway house, a pension run by a doctor named Denis Louis Grégoire Faltrier at 84 through 86 Rue de l'Ourcine, in what is now the 13th arrondissement. Faltrier's establishment was a hybrid between a medical facility and a boarding house where politically inconvenient prisoners could be monitored with less overhead than a full prison. It was at Faltrier's that Galois met Stéphanie Félicie Poterin du Motel, born in 1812. The identification comes from the work of Carlos Alberto Infantozzi, published in the Revue d'Histoire des Sciences in 1968, Volume 21, Number 2, a paper titled Sur la mort d'Évariste Galois. Infantozzi deciphered a partially erased name on the back of a letter in Galois' manuscripts at the Institut de France. The name reads Stéphanie du Motel. Later research by Olivier Courcel for the CNRS Images des Maths project traced her full name and subsequent biography. She was the daughter of Jean-Louis Poterin du Motel, a physician, and she lived at or near Faltrier's establishment. She married Charles Auguste Barrieux in 1840, lived later in Wallachia, and is buried at Montparnasse Cemetery. What happened between them is a gap in the record that no historian has been able to fill with certainty. What we know is that by mid-May of 1832, it was over. On May 14, Stéphanie wrote Galois a letter that survives only in fragments, because Galois copied portions of it onto his own manuscripts. From those fragments, it reads like a clear and firm rejection, and Galois' reaction was volcanic. On the backs of mathematical manuscripts, Over and over, he wrote, Stephanie, 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 surrounded by crude doodles of hearts. The juxtaposition is almost unbearable. On one side of the page, the foundations of abstract algebra. On the other side, a lovesick boy doodling a girl's name. And somewhere in the wreckage of that rejection, a duel was arranged. I want to be honest about what we know and what we do not know about the duel, because the mythology has grown so thick around this event that separating fact from legend requires care. What we know for certain comes from Galois himself. On the night of May 29th, 1832, he wrote 3 letters. The first was addressed to his Republican comrades. I have been provoked by 2 patriots. It was impossible for me to refuse. I beg forgiveness of all those I know for not having been able to say goodbye. In a second short letter, I die the victim of an infamous coquette and her 2 dupes. I was provoked by 2 patriots. Forgive those who kill me, for they were acting in good faith. 2 patriots, an infamous coquette, 2 dupes. The wording is specific enough to construct a rough picture. The duel was over Stephanie. The opponents were fellow Republicans, not royalist agents, and Galois went into it with what reads like resignation. The identity of the opponent. Alexandre Dumas, who knew Galois personally and had been at the May 1831 banquet, named the opponent in his mess memoirs as Pichot d'Herbenville. D'Herbenville was a fellow Republican patriot who had been acquitted alongside Galois in the trial of the 19. The Italian researcher Marco Fulvio Barozzi located a manuscript at the Bibliothèque Nationale de France, a copy of the 1791 Constitution inscribed with a note identifying d'Herbenville as the man who killed Galois in a duel. That is the strongest contemporary corroboration of Dumas. But a Lyon newspaper, Le Précurseur, published a notice on June 4th and 5th, 1832, referring to the adversary only by the initials L.D. Some historians have linked those initials to Ernest du Châtelet, another Republican who had shared Galois' imprisonment. And then there is E.T. Bell's version, published in 1937, which claims the duel was a political assassination arranged by royalist agents who used Stephanie as bait. Bell's version is dramatic. It is also, as Tony Rothman demonstrated in his 1982 article, Genius and Biographers, the fictionalization of Évariste Galois in the American Mathematical Monthly, Volume 89, almost entirely unsupported by evidence. Bell invented or exaggerated numerous details, and his account has poisoned the well of popular understanding ever since. The most defensible position, synthesizing Borgne's critical edition of the manuscripts, Rothman's debunking of Bell, and Courcell's biographical research, is this: the duel was real, not a conspiracy. It was fought over Stephanie. The opponent was probably d'Herbenville, possibly du Châtelet, almost certainly a fellow Republican. Galois went into it expecting to die. His letters of May 29th read like the letters of a man settling his affairs. And those letters included the mathematical testament, the night of May 29th, 1832. This is the night that Bell mythologized and that the myth has obscured. Bell wrote that Galois, in a frenzy of last-minute inspiration, scrawled the entirety of group theory in a single night of feverish composition, inventing the field from nothing as death approached. It is a magnificent story. It is also false. Peter Newman's definitive 2011 edition of the Mathematical Writings of Évariste Galois, published by the European Mathematical Society, makes the timeline clear. The substance of Galois theory, the premier memoir, had been submitted to Poisson In January 1831, over a year before the duel, the ideas had been developing since at least 1829. What Galois wrote on the night of May 29 was not an invention. It was a testament, a last, compressed summary of work he had been developing for 3 years and that nobody had been willing to read. But the letter contains material the submitted papers do not. The 7 pages Galois addressed to Chevalier that night divide in Neumann's edition into 3 sections. The first, roughly 2 pages, are a summary of the solvability theorem, the Galois group, the criterion for solvability by radicals, the key theorems of what is now called Galois theory. Dense, compressed, but covering ground already laid in the premier memoir. The second section, approximately 2 pages, contains results that go beyond the submitted work, results on modular equations. On what is now called PSL2P, the projective special linear group over the finite field of P elements, Galois proved that the modular equation of degree P plus 1 for P prime cannot be reduced below degree P except when P equals 5, 7, or 11. 3 exceptions. Just 3. And those 3 exceptional cases later turned out, in the work of Felix Klein in the 1870s, to correspond to the rotation groups of the 3 Platonic solids, the tetrahedron, the octahedron cube pair, and the icosahedron dodecahedron pair. He found the geometry of the Platonic solids hiding inside the algebra of modular equations in a prison transfer facility at the age of 20. And then the final section, 2.5 pages, the section Galois titled The Theory of Ambiguity. And this is the part that is genuinely haunting, because nobody understood it in 1832. Nobody understood it in 1846, when Liouville published the manuscripts. Nobody fully understood it for over a century. In these pages, Galois sketched the application of his symmetry methods to transcendental analysis, to the integration of algebraic functions, to what would later be recognized as the theory of Riemann surfaces and monodromy. Bernhard Riemann would not publish his dissertation on what we now call Riemann surfaces until 1851. Galois was seeing through polynomial algebra, all the way through to the topology of complex functions in 1832. The structures he was gesturing toward would not be fully engaged until Alexander Grothendieck's revolution in algebraic geometry in the 1960s. And in the margin, beside this section, the annotation that has become the most famous marginal note in the history of mathematics. Il y a quelque chose à compléter dans cette démonstration. Je n'ai pas le temps. There is something to complete in this proof. I have not time. The German-American mathematician Hermann Weyl, one of the great mathematical physicists of the 20th century, a man who himself made foundational contributions to group theory and quantum mechanics, later wrote of this letter. This letter, if judged by the novelty and profundity of ideas it contains, is perhaps the most substantial piece of writing in the whole literature of mankind. The most substantial piece of writing in the whole literature of mankind, written in a single night by a 20-year-old who would be dead by morning. In a letter to a friend, because no institution would publish it. At the end of the letter, Galois wrote, Tu prieras publiquement Jacobi ou Gauss de donner leur avis, non sur la vérité, mais sur l'importance des théorèmes. Après cela, il y aura, j'espère, des gens qui trouveront leur profit à déchiffrer tout ce gâchis. Je t'embrasse avec effusion. You will publicly ask Jacobi or Gauss to give their opinion, not on the truth, but on the importance of these theorems. After that, there will be, I hope, people who will find it to their advantage to decipher all this mess. I embrace you with all my heart. Then he sealed the letter. He sealed the manuscripts, and at dawn on May 30th, 1832, he walked out to a field near the Étang de la Glacière, south of the city. The duel was fought with pistols at 25 paces, standard distance for a French pistol duel of the period. Galois was shot in the abdomen. The ball perforated the intestine. Both seconds abandoned the scene. This was not unusual for illegal duels, which could result in prosecution. A passing peasant found Galois on the ground and had him transported to Hôpital Cauchy. He survived through the day and into the night. His brother Alfred arrived. According to the accounts that have been passed down, Galois refused the services of a priest. To Alfred, weeping at his bedside, he said the words that became his epitaph. Ne pleure pas, Alfred. J'ai besoin de tout mon courage pour mourir à 20 ans. Do not cry, Alfred. I need all my courage to die at 20. On May 31st, 1832, at approximately 10 in the morning, Évariste Galois died of peritonitis. He was 20 years and 7 months old. He was buried on June 2nd in a common grave at Montparnasse Cemetery. The location of the grave is now lost. Hundreds of Republicans attended the funeral, and it became a rallying point for the movement. The planned insurrection was postponed 3 days to June 5th, when the funeral of the Liberal General Lamarck provided a larger crowd. That insurrection, the June Rebellion of 1832, is the one depicted in Victor Hugo's Les Misérables. The barricades, the students, the doomed fight. It began, in a real and documented sense, at the graveside of a mathematician whose work nobody had read. And then, the silence. Chevalier did what Galois asked. In September of 1832, he published the testamentary letter and a short necrology in the Revue Encyclopédique, volume 165, pages 744 to 754. He publicly requested that Jacobi and Gauss give their opinions on the importance of the theorems. Jacobi was in Königsberg, Gauss was in Göttingen. Neither ever responded. Not a letter, not an acknowledgement, not a single word from either of the two greatest mathematicians then living about the work of the 20-year-old whose dying wish had been that they read it. And the manuscript sank. Alfred Galois, Évariste's younger brother, preserved them with the obsessive care of someone who understood that the papers mattered even if he could not understand why. Chevalier made fair copies, now bound in the Galois dossier at the Institut de France, but the mathematical community did not engage. For a decade, nothing happened. To understand what was lost during those years, you need to understand what the mathematics actually says. And I need to take you inside that now, because without understanding what Galois found, the rest of this story is just a biography, and it is not a biography. It is something much larger. The problem Galois was working on goes back 4,000 years. It is the oldest problem in algebra. It sounds simple. Given a polynomial equation, can you write down the solutions? A polynomial equation is a thing like x squared minus 5x plus 6 equals 0. That one is easy. The solutions are 2 and 3. You can find them by factoring. For more complicated quadratics, you use the quadratic formula, the one you learned in school. Negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. That formula has been known since the Babylonians carved it onto clay tablets around 1800 BCE. For any quadratic equation, no matter how ugly the coefficients, you plug them into the formula and out come the solutions. But what about higher degree equations? Cubics, degree 3. Quartics, degree 4. Can you always write down a formula? For cubics, The answer took 2,000 years to find. In the 1530s, in the Italian city-states, 3 mathematicians cracked it in one of the most dramatic episodes in the history of mathematics. Scipione del Ferro found the formula first, but kept it secret. Niccolò Tartaglia rediscovered it independently, and Girolamo Cardano published it in his 1545 book Ars Magna, The Great Art, over Tartaglia's furious objections. The cubic formula exists. It is ugly. It involves cube roots and square roots nested inside each other. But it works. For quartics, degree 4, Cardano's student Lodovico Ferrari found the formula in 1540. Even uglier than the cubic, but it works. By the mid-1500s, mathematicians had formulas for degrees 2, 3, and 4. The natural assumption was that degree 5 would follow. It was just a matter of cleverness. 300 years passed. Euler tried, Lagrange tried, Tschirnhaus tried, Bezout tried. Ruffini made a serious attempt in 1802, producing a proof of impossibility that was almost, but not quite complete. Nobody could find the Quintic formula, and the reason nobody could find it is that it does not exist. Abel proved this in 1824. His 6-page pamphlet, self-published in Christiania, is one of the turning points in the history of mathematics. The general 5th-degree polynomial equation cannot be solved by radicals. There is no formula that takes the coefficients of an arbitrary quintic and produces the roots using only addition, subtraction, multiplication, division, and the extraction of nth roots. Not because we are not clever enough, because the mathematical structure of the equation forbids it. Abel's proof was expanded and published in Crell's journal in 1826. It is rigorous and correct. It answered a question that had been open for 3 centuries, and it is incomplete in a way that almost nobody talks about. Because Abel proved that the general quintic has no radical solution. He proved that there is no universal formula that works for all quintics, but not every quintic is unsolvable. The equation x to the 5th minus 1 equals 0 has solutions that can be expressed in terms of radicals, the 5th roots of unity. You can write them down using square roots and 5th roots, so some quintics can be solved and some cannot. And Abel's theorem gives you no way to tell which is which. It is like proving that not every locked door can be opened with the same key, without telling you anything about which doors have keys and which do not. This is the problem Galois solved. And his solution was not just an improvement on Abel's, it was a completely different way of thinking about mathematics, a way of thinking that would take the mathematical community 40 years to absorb, and that would ultimately restructure not just algebra, but all of modern physics. Here is the idea. I am going to give it to you as close to the way Galois himself conceived it as I can, because his original formulation is actually more intuitive than the way most modern textbooks present it. Take a polynomial equation. Say it has 5 roots, 5 values of x that make the equation true. Call them Rn1, R2, R3, R4, R5. These roots live in some number system that might be bigger than the rational numbers. They might involve square roots, or cube roots, or 5th roots. The question is, which operations did you need to perform to get from the rationals to these roots? Now, here is Galois' key insight. The roots of the equation have relationships between them. Algebraic relationships. Equations involving the roots that are true because of the structure of the original polynomial. For example, the sum of all the roots equals the negative of the coefficient of x to the 4th divided by the leading coefficient. That is a relationship. The product of all the roots equals plus or minus the constant term. That is another relationship. There are subtler relationships too, involving pairs and triples and combinations of roots. Now imagine rearranging the roots, swapping RA1 and R2, or cycling Rn1 to R2, R2 to R3, R3 to R1. Some of these rearrangements will preserve every algebraic relationship between the roots. The sum will still be the same. The product will still be the same. Every equation relating the roots that was true before the rearrangement will still be true after. Other rearrangements will break the relationships. They will produce combinations that are algebraically false. The collection of all rearrangements that preserve every algebraic relationship is what Galois called the group of the equation. He used the word group. It is the first systematic use of this word in mathematics in anything resembling its modern meaning. Cauchy had done earlier work on permutations, but Galois formalized the concept of a group as a closed collection of operations, closed under composition, containing an identity, and containing an inverse for every element. The basic mathematical structure that an entire civilization of mathematics and physics would be built on. And here is the theorem. The polynomial equation is solvable by radicals if and only if its Galois group has a specific structural property. The group must be what Galois called solvable, meaning it can be decomposed into a chain of progressively smaller pieces, each one fitting neatly inside the one above it, with the layers between them being simple cyclic structures. If the group can be peeled apart this way, like an onion with neat concentric layers, the equation can be solved. If the group contains a core that cannot be peeled apart, a simple non-abelian piece that resists decomposition, then the equation cannot be solved by radicals. For degree 5, the symmetric group on 5 elements, the group of all possible rearrangements of 5 objects, contains the alternating group on 5 elements, which is simple and non-abelian. It cannot be decomposed. Therefore, the general quintic cannot be solved. But specific quintics, whose Galois groups happen to be solvable, can be. Abel said, the general quintic is unsolvable. Galois said, I can tell you for any equation of any degree, whether it is solvable or not, and the answer depends entirely on the hidden symmetry structure beneath the equation. He did not just answer the question. He revealed that the question was a shadow of a deeper architecture, an architecture built from symmetry. I need to pause here because I think the sheer strangeness of this gets lost in the abstraction. Let me make it concrete. Think about a square, a physical square drawn on a piece of paper. You can rotate it 90 degrees and it looks the same. You can rotate it 180 degrees and it looks the same. You can flip it along a diagonal and it looks the same. There are exactly 8 operations you can perform on a square that leave it looking identical to how it started. 4 rotations, including the do-nothing rotation, and 4 reflections. Those 8 operations form a group. They are closed under composition, meaning if you do one and then do another, the result is always equivalent to one of the 8. There is an identity element, the do-nothing rotation, and every operation has an inverse, another operation that undoes it. This is the dihedral group of order 8. A group. Now think about an equilateral triangle. 6 symmetry operations. 3 rotations, 3 reflections. The dihedral group of order 6. A different group. And if you compare the internal structure of these 2 groups, the way the operations compose with each other, the way they nest into subgroups, you find that the triangles group and the squares group have fundamentally different architectures. The triangle's symmetry group is solvable. The square's symmetry group is solvable. In fact, every symmetry group you can build from shapes in 2 dimensions is solvable. But when you move to permutations of 5 or more objects, something new appears. The alternating group on 5 elements, the group of even permutations of 5 objects, has 60 elements, and it is simple. It cannot be broken down into smaller pieces. It has no internal structure that you can peel apart. And because it is simple and non-abelian, any group containing it is not solvable. This is the obstruction. This is the wall. The reason the general quintic cannot be solved by radicals is not that the formula is too complicated. It is that the symmetry structure of the equation contains an indecomposable core, a nugget of irreducible complexity that cannot be unwound by any sequence of root extractions. The wall is not computational. It is structural. It is architectural. And Galois saw this at 19. He saw that beneath every equation lies a hidden structure, and that the properties of that structure determine what the equation can and cannot do. He saw that algebra is not about computation. Algebra is about architecture. And that insight, that specific insight, is what makes everything that follows in physics possible. Because physics, it turned out, is also not about computation. Physics is about architecture, the architecture of symmetry. And the concept at the center of that architecture, the group, turned out to be the most portable and powerful mathematical object ever discovered. Because groups do not just describe the symmetry of equations, groups describe symmetry itself. Any symmetry, the symmetry of a snowflake, the symmetry of a crystal lattice, the symmetry of space and time, the symmetry of the fundamental forces of nature. Anywhere there is a transformation that leaves some structure unchanged, there is a group. And the study of that group tells you what is really going on underneath the surface. Galois could not have known any of this in 1831. He was solving equations. He was working in pure algebra. The application to physics was a century away. But the mathematics he found was not just useful for physics. It was the language of physics, the thing without which physics cannot be stated. And that, I think, is the deepest mystery in this entire story. Not the tragedy, not the negligence. The mystery of why a mathematical structure invented to analyze polynomial roots turned out to be the structure of physical reality. But we are getting ahead of the story. Because in 1832, with Galois dead and the manuscripts in the hands of Chevalier and Alfred, the architecture was invisible. It existed on paper, paper that nobody would read for 14 years. The silence lasted from 1832 to 1846. 14 years, during which the most powerful mathematical framework in existence sat in drawers and filing cabinets, and the personal collections of men who knew the papers mattered, but could not find anyone to read them. During those 14 years, mathematics continued without Galois, and I want to be specific about what that cost, because the phrase delayed progress does not capture the scale of the loss. Cauchy, who had redirected Galois' manuscript to Fourier's desk in the first place, published prolifically on analysis and permutation theory throughout the 1830s and 40s. His 1844 and 1845 papers on arrangements developed a theory of permutation groups that ran parallel to Galois's, but was less powerful, less general, and less connected to the theory of equations. Cauchy was reinventing a wheel that already existed. Worse, he was reinventing a cruder version of it. Had he read the paper he redirected 15 years earlier, his own work would have started from a higher baseline and reached further. In Berlin, Peter Gustav Lejeune Dirichlet was developing analytic number theory, creating connections between analysis and the distribution of prime numbers. His work would have benefited enormously from Galois' theory of finite fields, the Galois Imaginaries, published in Ferrasac's Bulletin in 1830, which gives a complete classification of fields with finitely many elements. Those fields are fundamental to number theory. Dirichlet worked without them. Ernst Eduard Kummer, beginning in the 1840s, developed his theory of ideal numbers to tackle problems in algebraic number theory, particularly his approach toward Fermat's last theorem. Kummer was trying to recover unique factorization in algebraic number fields where it fails. His ideal numbers were brilliant, and they were the ancestors of what Dedekind would later formalize as ideals. But Galois theory illuminates the structure of these number fields directly. It tells you how the field is constructed, what its symmetries are, how it relates to the rationals. Kummer was building elaborate scaffolding to reach a window that Galois theory opens from the inside. And in England, Arthur Cayley and James Joseph Sylvester were developing invariant theory, the study of algebraic expressions unchanged under certain transformations. This is group theory, wearing a disguise. Cayley eventually introduced the abstract concept of a group in 1854, 22 years after Galois' death, but his definition was less powerful and less connected to the theory of equations than the framework Galois had already built. None of these mathematicians knew what they were missing. That is the cruelest part. The work was invisible. It existed on paper, in a drawer, in the hands of Chevalier and Alfred, who could not find anyone to read it. The mathematical community was solving problems with inadequate tools, because the adequate tools had been invented, written down, submitted for evaluation, rejected, and buried. How the manuscripts reached Liouville is itself a story that has never been fully reconstructed. The chain of custody runs from Galois to Alfred and Chevalier in 1832, and then somehow to Joseph Liouville around 1842. Lutzon's 1990 biography of Liouville canvasses several theories, but reaches no definitive conclusion about the exact path. What is certain is that Liouville read the manuscripts with the care that Poisson had not, and Liouville, unlike Poisson, saw what was there. On September 4th, 1843, 11 years after Galois' death, Liouville announced to the Académie des Sciences, "I have found in the papers of Galois a solution as exact as it is profound of this beautiful problem. Given an irreducible equation of prime degree, to decide whether or not it is soluble by radicals. A solution as exact as it is profound." Those are the words Liouville used to describe the work that Poisson had called neither sufficiently clear nor sufficiently developed. The same mathematics, 12 years apart. One referee said it was incomprehensible. Another said it was a solution as exact as it is profound. The only variable that changed was the referee. And then Liouville sat on it for 3 more years. Why? I have read multiple accounts, and I still do not find a fully satisfying explanation. The charitable version is that Liouville was preparing a careful edition and wanted to fill what he called some slight gaps in the proofs before publishing to ensure the mathematics was bulletproof. The less charitable version, which some historians have suggested, is that publishing the mathematical testament of a Republican martyr whose funeral had helped spark the 1832 June Rebellion was politically inconvenient under the July monarchy of Louis Philippe, the same king that Galois had toasted with a dagger above his cup. The 1840s were a period of political tension in France, and celebrating dead revolutionaries was not career-enhancing at the Academy. Whatever the reason, the publication came in October and November of 1846. The Œuvres mathématiques d'Évariste Galois, published in the Journal de Mathématiques Pures et Appliquées, Tome 11, pages 381 through 444, 64 pages. Liouville's preface titled Avertissement. The previously published articles from Gergon's Analyse and Ferrasac's Bulletin, the testamentary letter, the premier memoir, and the fragment of the second memoir on primitive equations. In the preface, Liouville described his vivid satisfaction at having recognized, after filling some slight gaps, the complete correctness of Galois' method. He wrote that everything not perfectly clear is not mathematics, and that Galois' work, once those gaps were filled, was mathematics of the highest order, 17 years after the first submission to Cauchy, 14 years after the death, the foundation of modern algebra, finally in print. And even then, comprehension was slow. The mathematics was so far ahead of its time that merely publishing it was not enough. It required translators, people who could take what Galois had compressed into 64 pages and expand it into a framework that other mathematicians could work with. The first was Enrico Betti in Italy, who in 1851 and 52 published papers giving the first rigorous proofs of key elements of Galois theory, establishing that the Galois group is genuinely a group of permutations in the modern sense. Then came Camille Jordan, whose 1870 book Traité des substitutions et des équations algébriques, the treatise on substitutions and algebraic equations, was the first textbook treatment of Galois theory. Jordan's trait made the ideas accessible to the broader mathematical community for the first time. It was published 38 years after the premier memoir was written. Richard Dedekind at Göttingen recast Galois theory in terms of fields and automorphisms in lectures delivered between 1856 and 58, giving the theory its modern algebraic formulation. Heinrich Weber's Lehrbuch der Algebra in 1895 refined it further, and Emil Artin's lectures in the 1940s gave us the clean, definitive formulation taught in graduate algebra courses today. The total elapsed time from Galois' first formulation of the theory in 1829 to Jordan's textbook making it widely available in 1870 was 41 years. 41 years during which the most powerful algebraic framework in existence was either buried, published but unread, or read but not understood. And Jordan's trait, when it finally appeared, was not a gentle introduction. It was 667 pages of dense, technical algebra. But it worked. It translated Galois' compressed, sometimes cryptic original writings into a systematic framework that other mathematicians could build on. Jordan clarified the concept of a normal subgroup. He developed the theory of composition series. He connected Galois' work on equations to the emerging theory of permutation groups that Cauchy had been developing independently. And most importantly, he showed the mathematical community that Galois had not just solved a specific problem. Galois had created a new way of thinking about algebra itself, a way of thinking that was structural rather than computational, that asked not what is the answer, but what is the shape of the space of possible answers. The impact, once mathematicians absorbed Jordan's presentation, was explosive. Within a decade, Galois theory had become central to algebraic number theory, to the study of Riemann surfaces, to invariant theory, and to the emerging field of abstract algebra. Dedekind at Göttingen recast the entire theory in terms of field extensions and automorphisms, the formulation taught today. He recognized that Galois groups were not just permutation groups, but automorphism groups, groups of symmetries of algebraic structures, and that this perspective unified the theory of equations with the theory of fields in a way Galois himself had only glimpsed. By the turn of the 20th century, group theory had become one of the central pillars of mathematics, and it was about to become one of the central pillars of physics. Because group theory did not stay inside algebra, it leaked out. It crossed the border into geometry through Klein's Erlangen program, then into continuous symmetry through Lie, and then it crossed into physics. And when it crossed into physics, it did not arrive as a useful tool. I think the mathematics community has never fully reckoned with this. The narrative has been absorbed into a story of romantic tragedy. The young genius, the duel, the lost manuscripts, the eventual vindication. And vindication makes it sound like the story has a happy ending. But the 41-year delay was not a harmless gap that was eventually filled. It was a loss, real mathematical progress that did not happen because the tools were locked in a cabinet. We cannot know what would have been different if Jordan's trait had appeared in 1835 instead of 1870. But we can know that it would have been different. And the people responsible for the delay, Poisson, who rejected it, Fourier, who died with it on his desk, Liouville, who sat on it for 3 years, Jacobi and Gauss, who never answered Chevalier's public plea, none of them were punished or even criticized. The cost was paid entirely by mathematics, but the cost, it turned out, was not limited to mathematics, because group theory did not stay inside algebra. It leaked out, it crossed the border into geometry, then into physics. And when it crossed into physics, it did not arrive as a useful tool. It arrived as the fundamental language, the thing without which the physics could not be stated. The crossing began almost immediately after Jordan's trait. In the 1870s, a Norwegian mathematician named Sophus Lie, working in close collaboration with Felix Klein, began extending Galois' ideas from finite groups with a countable number of elements, to continuous groups whose elements formed smooth surfaces in mathematical space. Galois groups are discrete. They shuffle roots around in a finite number of ways. Lie groups are continuous. They represent smooth transformations, rotations, dilations, the kinds of symmetry operations you can perform on geometric objects. Lie was inspired directly by Galois and Jordan. He wanted to do for differential equations what Galois had done for polynomial equations, classify them by their symmetry groups. The resulting theory, Lie group theory, became one of the central structures of modern mathematics, and its applications went far beyond differential equations. In 1872, Felix Klein, at the age of 23, published his Erlangen program, a manifesto that redefined geometry itself in terms of group theory. Klein's insight was that every geometry can be characterized by a group of transformations that preserve its fundamental properties. Euclidean geometry is the study of figures unchanged by rotations, reflections, and translations. Projective geometry is the study of figures unchanged by projective transformations. Hyperbolic geometry, elliptic geometry, affine geometry, each one defined by its symmetry group. Klein unified all of geometry under the umbrella of group theory. The concept Galois had invented to study polynomial equations had swallowed geometry whole. And then it swallowed physics. The bridge was built by a woman who was barred from the institution that would have been her natural home. Amélie Emmy Noether, born March 23, 1882, in Erlangen, Bavaria, the daughter of the mathematician Max Noether. She completed her doctorate at the University of Erlangen in 1907 with a dissertation on algebraic invariant theory. At a time when women in Bavaria could audit university courses but were not officially admitted as regular students, she was allowed to sit the examination only because the rules had been changed the previous year. In 1915, David Hilbert and Felix Klein, the two most powerful mathematicians in Germany, invited Noether to Göttingen. Hilbert was working on the mathematical foundations of Einstein's general relativity and needed her expertise in invariant theory. The philosophy faculty objected. A woman as a faculty member, one professor reportedly asked what the returning soldiers would think when they learned they had to study at the feet of a woman. Hilbert's response has entered mathematical legend. I do not see that the sex of the candidate is an argument against her admission as a private docent. After all, we are a university, not a bathhouse. The faculty was unmoved. For 4 years, Noether lectured at Göttingen under Hilbert's name. Her courses listed in the university catalogue as Professor Hilbert, with the assistance of Fraulein Noether. She was unpaid. She had no official position. She survived on a small inheritance and whatever income she could scrape together. And in 1918, working within this exclusion, she proved the theorem. Invariant variations problem. Invariant variation problems. Presented on July 16, 1918, to the Göttingen Königliche Gesellschaft der Wissenschaften by Felix Klein, because Noether could not present it herself, because she was not a member, because she was a woman. Published in the Nachrichten of the Gesellschaft. The theorem is one of the most important results in the history of physics. It states, for every continuous symmetry of the action, there exists a corresponding conserved quantity. I need to unpack that because the sentence sounds technical and the reality is seismic. The action in physics is a mathematical quantity that encodes the dynamics of a system. You can think of it as a function that takes in a possible history of a system, how it moves through space over time, and spits out a number. The actual history of the system, what really happens, is the one that makes the action stationary. Roughly speaking, the one that makes the action as small as possible. This is the principle of least action, one of the deepest organizing principles in physics, known since Euler and Lagrange in the 18th century. A symmetry of the action means a transformation you can perform on the system that does not change the action's value. If you shift the entire system forward in time by 1 second and the action does not change, that is a symmetry. Time translation symmetry. If you slide the entire system sideways in space and the action does not change, that is spatial translation symmetry. If you rotate the entire system and the action does not change, that is rotational symmetry. What Noether proved is that each of these symmetries automatically produces a conserved quantity. Time translation symmetry gives you conservation of energy, not as a separate law, not as an additional postulate, as a mathematical consequence. If the laws of physics are the same today as they were yesterday, energy is conserved. Period. It cannot not be conserved. The symmetry guarantees it. Spatial translation symmetry gives you conservation of momentum. If the laws of physics are the same here as they are a meter to the left, momentum is conserved. Rotational symmetry gives you conservation of angular momentum. And here is where it reaches into the structure of matter itself. If there is a more abstract kind of symmetry, a symmetry of the quantum mechanical phase, a U1 symmetry, then Noether's theorem gives you conservation of electric charge. Charge conservation is not a separate law of nature. It is a mathematical consequence of an internal symmetry of the quantum fields. Think about what this means for your actual physical life. Right now, as you listen to this, the sodium and potassium ions flowing through the channels in your neurons are governed by the conservation of electric charge. Those ions carry signals from one neuron to the next. Those signals produce your thoughts, your perceptions, your experience of being alive. And the reason those ions behave the way they do, the reason charge is conserved, is not because God decreed it, or because it is a brute fact with no explanation. It is because the underlying quantum field has a U1 phase symmetry, a symmetry described by a group, the concept of which was formalized by Galois. The chain runs from Galois to your consciousness. That is not a metaphor. That is a mathematical fact. The conservation of charge, which governs the electrochemistry of your brain, is a Noether consequence of a gauge symmetry, which is described by a Lie group, which is the continuous extension of a finite group, which was defined by Évariste Galois in a paper that Simeon Denis Poisson could not understand. The mathematics in your skull is older than the physics that describes your skull. And Noether herself, the person who built this bridge, never received a proper faculty position at Göttingen. She was finally granted the right to lecture under her own name in 1919. A year after the theorem, she was appointed as an associate professor without tenure in 1922. Her salary was small. Her recognition was minimal relative to the magnitude of what she had done. When the Nazis came to power in 1933, she was dismissed from Göttingen under the law for the restoration of the professional civil service, which barred Jews from academic positions. She emigrated to the United States and took a position at Bryn Mawr College and at the Institute for Advanced Study in Princeton. She died on April 14, 1935, at the age of 53, of complications following surgery. Einstein wrote in a letter to the New York Times that Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. Another outsider, another genius barred by institutional authority from the recognition she deserved, another person who saw a piece of the architecture and could not get the establishment to look at it until decades after the work was done. The pattern is not incidental. The pattern is structural, and it connects Galois to Abel, to Noether in a chain of institutional failures that stretches across a full century. Every conservation law in physics, every single one, is a Noether consequence of a continuous symmetry, and the mathematical framework for describing continuous symmetries is Lie group theory, which is the continuous extension of the finite group theory that Galois invented. The chain is direct. Galois defined groups, Jordan systematized them, Lie extended them to continuous symmetries, Klein used them to define geometry, and Noether used them to define physics. Each link forged by someone the establishment initially resisted, and the chain was about to extend further. In 1954, two physicists at the Institute for Advanced Study in Princeton, Chen-Ning Yang and Robert Mills, published a paper in Physical Review, volume 96, pages 191 through 195. The title was Conservation of Isotopic Spin and Isotopic Gauge Invariance. The paper was 4.5 pages long, and it contained the mathematical structure that would eventually describe every force in the universe, except gravity. What Yang and Mills did was take a concept that had been implicit in electromagnetism since Maxwell and make it explicit, and then generalize it. In electromagnetism, the physics is invariant under a certain kind of phase transformation, a U1 gauge transformation. You can multiply the wave function of a charged particle by a complex number of unit magnitude, a phase factor, and the physics does not change. This is U1 gauge symmetry, and by Noether's theorem, it gives you charge conservation. Yang and Mills asked, what happens if you make this symmetry non-abelian? What happens if, instead of the simple number rotating group U1, you use a more complex group like SU2, where the order of operations matters. They showed that promoting a global C2 symmetry to a local gauge symmetry, requiring the physics to be invariant under C2 transformations that can vary from point to point in space and time, forces you to introduce new fields, gauge fields, fields that mediate the interaction between particles, the way the electromagnetic field mediates the interaction between charges. The mathematical language Yang and Mills used was the language of principal fiber bundles and connections with non-abelian structure groups. Every word in that description traces back to group theory, to Lie groups, to Galois. Yang presented this work at a seminar at the Institute for Advanced Study in February of 1954. Wolfgang Pauli was in the audience. Pauli, one of the sharpest and most ruthless critics in all of physics, immediately zeroed in on a problem. The gauge bosons in Yang-Mills theory had to be massless because gauge symmetry forbids a mass term. But the short range of the nuclear forces implied that the force-carrying particles had to be massive. How did Yang intend to solve this? Yang did not have an answer. He sat down. The room was silent. Pauli had identified a fatal flaw, or what appeared to be a fatal flaw, in the most important theoretical proposal since quantum electrodynamics. And for 10 years, Yang-Mills theory existed in a kind of mathematical limbo, beautiful, structurally perfect, and apparently inapplicable to the real world because it predicted massless particles that did not exist. This is worth pausing on, because the pattern is so familiar, it has become almost a cliché in the history of physics, except that recognizing it as a cliché does not make it less important. A new mathematical framework is proposed. It is elegant, it is structurally inevitable, meaning it follows naturally from the deepest principles of the existing theory, and the establishment says it cannot work because it predicts something we do not observe. The framework sits in limbo. Years pass, sometimes decades, and then someone finds the missing piece that resolves the apparent contradiction, and the framework turns out to be correct after all. This happened with Copernicus. It happened with Boltzmann. It happened with Dirac. And it happened with Yang-Mills. The missing piece, when it came, was the mechanism of spontaneous symmetry breaking. The idea, developed independently by several groups in 1964, is subtle and beautiful. The fundamental equations of the theory respect the full gauge symmetry, but the ground state, the vacuum, the lowest energy configuration of the fields, does not. The vacuum spontaneously chooses a direction in the internal symmetry space, the way a ball balanced on top of a hill spontaneously rolls down to the bottom and picks a direction. The underlying physics is symmetric, but the observable state is not. And when this happens in a gauge theory, the gauge bosons that were massless in the symmetric phase acquire mass from their interaction with the Higgs field. The symmetry is not broken in the equations, it is broken in the solution. And the mass terms that Pauli demanded are generated not by hand, but by the dynamics of the theory itself. The resolution came in 1964, with the papers by Peter Higgs in Edinburgh, François Englert and Robert Brute in Brussels, and Gerald Guralnick, Carl Richard Hagen, and Tom Kibble at Imperial College London. 6 physicists, 3 independent papers, all converging on the same mechanism. And in 1971, Gerard Hooft, then a 25-year-old graduate student at Utrecht working under Martinus Veltman, proved the decisive theorem that Yang-Mills theories with spontaneously broken symmetry are renormalizable, producing finite predictions at all energies. His paper, Renormalizable Lagrangians for Massive Yang-Mills Fields, published in Nuclear Physics B Volume 35, unlocked the entire framework. Veltman and 't Hooft shared the 1999 Nobel Prize for this work. And then Murray Gell-Mann showed the world what it could do. Gell-Mann, born September 15, 1929, in Manhattan, entered Yale at 15, completed his PhD at MIT at 21 under Victor Weisskopf. By the late 1950s, he was at Caltech, and he was staring at a problem that had been driving particle physicists to despair: the zoo. Throughout the 1940s and 50s, experimentalists using cosmic ray detectors and the early particle accelerators had discovered a bewildering variety of subatomic particles. The proton and neutron were only the beginning. There were pions, kaons, lambda particles, sigma particles, eta mesons, dozens of supposedly fundamental particles with no obvious organizing principle. The situation was so chaotic that Enrico Fermi reportedly joked that if he had wanted to memorize the names of particles, he would have become a botanist. Gell-Mann found the organizing principle. In March of 1961, he published a Caltech synchrotron laboratory report, CTSL 20, titled The Eightfold Way, a theory of strong interaction symmetry. The Israeli physicist Yuval Ne'eman independently developed the same framework at around the same time. What they found was that the proliferating particles could be organized into geometric patterns corresponding to representations of the Lie group SU3, the special unitary group in 3 dimensions, a continuous symmetry group, a direct descendant of Galois's concept. The 8 lightest baryons, the proton, the neutron, the lambda, the 3 sigma particles, and the 2 xi particles fit into an 8-dimensional representation of SU3 called the adjoint representation, forming an octagonal pattern that Gell-Mann, with characteristic flair, named after the Buddhist Noble Eightfold Path. The mesons similarly organized into an octet. Particles that had seemed random now fell into precise geometric arrangements dictated by group theory. And then the decuplet. 10 spin 3/2 baryons, heavier cousins of the proton and neutron, could be arranged in a triangular pattern corresponding to the 10-dimensional representation of SU3. By late 1962, 9 of the 10 slots in the decuplet were occupied by experimentally observed particles. The 10th slot, at the apex of the triangle, was empty. Gell-Mann stood up at the 1962 International Conference on High-Energy Physics in Geneva and made a prediction. The empty slot, he said, would be filled by a particle with specific properties dictated entirely by the group theory. Strangeness, -3. Electric charge, -1. Spin, 3/2. And a mass that the Gell-Mann-Okubo mass formula, derived from the SU3 representation structure, predicted at approximately 1685 mega-electronvolts. He called it the omega minus. The prediction was specific. It was falsifiable. It was derived entirely from the symmetry structure of SU3. If the particle existed at roughly the predicted mass, the eightfold way was confirmed, and group theory was the language of the strong force. If it did not, the entire framework collapsed. The search began almost immediately. At Brookhaven National Laboratory on Long Island, a team led by Nicholas Samios designed an experiment using the alternating gradient synchrotron, a particle accelerator that could produce beams of negative kaons with enough energy to create strangeness negative, 3 particles if they existed. The detector was an 80-inch liquid hydrogen bubble chamber, a vessel filled with superheated liquid hydrogen in which charged particles leave visible tracks of tiny bubbles as they pass through. On January 31st, 1964, After analyzing approximately 100,000 bubble chamber photographs, one by one, frame by frame, scanning each image for the telltale cascade of particle tracks that would signal the creation and decay of the omega minus, the team found a candidate event. I want you to picture the bubble chamber photograph, because it is one of the most important images in the history of physics. The chamber is filled with liquid hydrogen, superheated just past its boiling point. When a charged particle passes through the liquid, it ionizes hydrogen atoms along its path, and tiny bubbles form along the trail of ionization. The bubbles are photographed from multiple angles, producing a three-dimensional record of every particle that passed through the chamber. The result looks like a tangle of curved lines, spirals, and forking paths. Each curve tells you the particle's charge, its momentum, and its mass, because the chamber sits inside a powerful magnetic field that bends charged particles, and the radius of the bend depends on the particle's momentum to charge ratio. In the candidate event, a negative kaon entered the chamber and struck a proton. The collision produced a cascade. First, the omega minus was created alongside a K plus and a K0. The omega minus, carrying strangeness -3, immediately decayed a xi0 and a pi minus. The xi0 decayed into a lambda and a pi 0. The lambda decayed into a proton and a pi minus. Each decay left its signature in the bubble tracks. Each track could be measured. Each measurement could be compared to the predictions. The mass of the omega minus, reconstructed from the momenta of its decay products, 1672 mega-electron volts. The prediction from the Gell-Mann Okubo mass formula, derived entirely from the SU3 decuplet representation theory, approximately 1685 mega-electron volts. Agreement within 1%. Within 13 mega-electron volts, a particle that had never been seen before, predicted from pure mathematics, found exactly where the group theory said it would be. Barnes et al. Submitted the paper to Physical Review Letters on February 11, 1964. Observation of a hyperon with strangeness -3. Physical Review Letters, Volume 12, page 204. When the paper was published, it was immediately recognized as one of the decisive experimental confirmations of a theoretical framework. The omega minus was to SU3 what the discovery of Neptune had been to Newtonian gravity, a prediction from pure theory, confirmed by observation, validating the entire mathematical structure that produced it. A particle that had never been seen before, predicted to exist with a specific mass and specific quantum numbers, purely from the representation theory of a Lie group, found in a bubble chamber photograph exactly where the mathematics said it would be. The prediction had been derived from SU3 symmetry. SU3 is a Lie group. Lie groups are the continuous extension of finite groups. Finite groups were formalized by Évariste Galois, the intellectual chain from the margins of a rejected manuscript in 1831 to a bubble chamber photograph on Long Island in 1964 is direct, traceable, and unbroken. Gell-Mann received the 1969 Nobel Prize in Physics for his contributions concerning the classification of elementary particles and their interactions. The Nobel citation does not mention Galois. No citation in particle physics has ever mentioned Galois, but every single argument in every citation in particle physics rests on mathematics that would not exist without him. And the omega minus was just the beginning of what the framework could do. The success of SU3 flavor symmetry led directly to the quark model. In 1964, the same year the omega minus was found, Gell-Mann proposed that the hadrons, the protons and neutrons, and all their heavier cousins were not fundamental particles at all. They were composite. They were made of more elementary constituents he called quarks, borrowing a word from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. George Zweig, working independently at CERN, proposed the same idea and called them aces. The quark model said that a proton is made of 2 up quarks and 1 down quark. A neutron is 2 downs and 1 up. The omega minus is 3 strange quarks. The entire zoo of hadrons, the bewildering menagerie that had driven Fermi to his botanist joke, could be explained as different combinations of a small number of fundamental quarks, organized by the representation theory of SU3. And each quark carries a new kind of charge, a charge that Gell-Mann named color, not because it has anything to do with actual color, because, like colors, it comes in 3 varieties: red, green, blue. The strong force between quarks is mediated by gluons, 8 of them, corresponding to the 8 generators of the Lie group SU3. This is quantum chromodynamics, QCD, the theory of the strong nuclear force. It is an SU3 gauge theory. The mathematics is Yang-Mills theory applied to the specific group SU3, and QCD was placed on rigorous theoretical footing in 1973 when David Gross, Frank Wilczek, and H. David Politzer discovered asymptotic freedom, the remarkable property that quarks interact more weakly at shorter distances and more strongly at longer distances, which explains why quarks are permanently confined inside protons and neutrons, and why the strong force has the peculiar character that it does. Gross, Wilczek, and Politzer shared the 2004 Nobel Prize. Meanwhile, the electroweak unification was being assembled in parallel. Sheldon Glashow, in a 1961 paper, proposed unifying electromagnetism and the weak nuclear force under the gauge group SU2 times U1. Steven Weinberg, in a 1967 paper in Physical Review Letters titled A Model of Leptons, and Abdus Salam, working independently in 1968, incorporated the Higgs mechanism into Glashow's framework, producing a complete, renormalizable theory of the electro-weak interaction. The W+, W-, and Z0 bosons were predicted with specific masses. Those masses were confirmed experimentally in 1983 at CERN, when Carlo Rubbia and Simon van der Meer's UA1 and UA2 experiments at the superproton synchrotron found the W at about 80 gigaelectron volts, exactly where the theory said they would be. Rubbia and van der Meer won the 1984 Nobel Prize. Glashow, Weinberg, and Salam had already shared the 1979 Nobel. Count the Nobel Prizes. 1969, Gell-Mann for the Eightfold Way. 1979, Glashow, Weinberg, Salam for electroweak theory. 1984, Rubbia and van der Meer for W and Z discovery. 1999, Tooft and Veltman for renormalization. 2004, Gross, Wilczek, Politzer for asymptotic freedom. 2013, Higgs and Englert for the mass mechanism. 6 Nobel Prizes in physics awarded to 14 physicists for work that is fundamentally and inescapably group theoretic. Every one of those prizes depends on gauge symmetry. Every one depends on Lie groups. Every one descends from the concept Galois formalized in Sainte-Pélagie prison at the age of 19. The result, assembled piece by piece through the 1960s and 70s, confirmed step by step through the 80s, 90s, and 2000s, is the standard model of particle physics. The gauge group SU, 3 times SU, 2 times U1. 3 symmetry groups, Three forces, SU3 for the strong color force, mediated by 8 gluons. SU 2 times U1 for the electroweak force, mediated by the W+, W-, Z0 bosons and the photon. Every elementary particle, every quark, every lepton, every gauge boson, classified by its representation under these groups. Every conservation law, charge, color, lepton number, baryon number, and Noether consequence of a continuous symmetry. Every interaction vertex, every Feynman diagram, every scattering amplitude, dictated by the gauge structure. The standard model has been tested to a precision that defies ordinary comprehension. The anomalous magnetic moment of the electron, the tiny deviation of the electron's magnetic properties from the value predicted by simple relativistic quantum mechanics, has been measured in experiments led by Gerald Gabrielse at Harvard, and agrees with a theoretical prediction from quantum electrodynamics to better than 1 part in a trillion. 1 part in a trillion. For scale, that is equivalent to predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. It is the most precise agreement between theory and experiment in the history of science, and the theoretical framework that produces this prediction rests on gauge symmetry, which rests on group theory, which rests on pages that were rejected as incomprehensible by the French Academy of Sciences in 1831. And the confirmations kept coming, right up to the present century. On July 4th, 2012, physicists at CERN announced the discovery of the Higgs boson, the particle associated with the Higgs mechanism of spontaneous symmetry breaking that had been predicted in 1964. The Higgs field is what gives mass to the W and Z bosons and to the fermions. Its existence was predicted entirely from the gauge structure of the standard model, from the requirement that the SU 2 times U1 electroweak symmetry be spontaneously broken. The measured mass of the Higgs boson, approximately 125 gigaelectronvolts, confirmed the mechanism. Peter Higgs and François Englert shared the 2013 Nobel Prize in Physics. That discovery, too, is a Galois descendant, because the Higgs mechanism is a mechanism of spontaneous symmetry breaking within a gauge theory. The gauge theory is defined by a symmetry group. The symmetry group is a Lie group, and Lie groups are the continuous extension of the concept Galois formalized. Every confirmation of the standard model, from the anomalous magnetic moment of the electron to the Higgs boson, is a confirmation that the mathematical framework a 20-year-old invented to study polynomial equations is the correct language for describing the fundamental structure of matter. Every single one. And I need you to understand something about the way physicists think about this, because it reveals how deep the dependence goes. In modern theoretical physics, you do not start with particles. You do not start with forces. You do not start with experiments. You start with a symmetry group. You write down the most general Lagrangian consistent with that symmetry group, and the particles, the forces, the interactions, the conservation laws, all of them fall out of the mathematics. They are consequences of the group structure. You choose the group and the physics follows. That means the group is more fundamental than the particles. The symmetry is more fundamental than the matter. A mathematical structure Galois defined in 1831 is not a description of reality. It is prior to reality. The particles exist because the symmetry exists. The forces exist because the gauge structure exists. The conservation laws exist because the symmetry is there. Remove the group theory and nothing remains. Not the electron, not the quark, not the photon, not you. That is not a poetic way of talking about physics. That is the literal mathematical content of the standard model. The group theory comes first. The physics is derived from it. The architecture precedes the building. I want to stop here and make sure you see the shape of what I have been building. Because the shape is not a straight line from Galois to the standard model. The shape is something more unsettling than that. Galois was not working on physics. He had no concept of particles, forces, gauge invariance, conservation laws, or the structure of matter. He was solving a pure mathematics problem about polynomial equations. He wanted to know which equations could be solved by radicals and which could not. That is all. It was a question in algebra, with no connection to the physical world that anyone in 1831 could have seen or imagined. And in answering that question, he invented a mathematical structure that turned out to be the structure of physical reality, not a useful tool for physicists, not a convenient formalism. The structure, the load-bearing architecture, the thing without which modern physics is not just incomplete, but inexpressible. You cannot state the standard model without group theory. You cannot write down the Lagrangian of the standard model without representations of Lie groups. You cannot derive a single prediction of quantum field theory without the gauge structure that Galois' concept makes possible. He did not build a tool that physicists later found handy. He found the architecture, and the architecture was already there, built into the fabric of physical reality a century before anyone knew what physical reality was made of. Eugene Wigner, the Hungarian-American Nobel laureate, who himself used group theory to classify the elementary particles by their representations under the Poincare group, wrote about this in a famous 1960 essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, published in Communications in Pure and Applied Mathematics, Volume 13. He wrote that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and that there is no rational explanation for it. He wrote that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. Wigner was talking about exactly this, about the fact that a dying boy's algebra turned out to be the grammar of matter, about the fact that mathematics does not merely describe the universe, it precedes the universe. And I want to be precise about what I mean by precedes, because it is not a metaphor. When Yang and Mills wrote down their gauge theory in 1954, they did not discover the gauge symmetry by doing experiments. They discovered it by following the mathematics. The mathematics told them what the symmetry had to be. The experiments came later and confirmed what the mathematics had already said. When Gell-Mann organized the hadrons into SU3 representations, he did not observe the symmetry in the data first and then find a group to describe it. He started with the group theory, wrote down the representations, and the particles fell into them. The prediction of the omega minus came from the mathematics. The experiment confirmed it. The math was first. And when Noether proved her theorem in 1918, she was not generalizing from experimental observations of conservation laws. She was proving a mathematical theorem about the structure of variational principles. The theorem says that if the action has a continuous symmetry, a conserved quantity must exist. It does not say observations suggest or experiments indicate. It says must. The conservation of energy is not an empirical finding that could, in principle, be overturned by a sufficiently clever experiment. It is a mathematical consequence of time translation symmetry. If the laws of physics do not change over time, energy is conserved. That is a theorem. It cannot be otherwise. The symmetry groups were there before the particles were. The conservation laws were encoded in the structure of the action before any experiment was performed. The architecture was there before the building was, and Galois saw it first. Not all of it, not even a large fraction of it, but the foundational piece, the concept that makes all the rest possible. The group, the hidden structure beneath the surface of equations, the idea that what matters is not the objects themselves, but the symmetries that relate them. He saw this at 19, in a country that was tearing itself apart politically, while attending a school that expelled him. After being rejected by the school he wanted, after watching his father destroyed by institutional malice, while submitting papers to referees who could not read them, he saw the skeleton of mathematics, and, through it, the skeleton of reality. And nobody around him could see what he was holding. And the question Wigner asked, the question I still do not know how to think about, is why the skeleton is there at all. Why does the mathematical structure of polynomial solvability have anything to do with the structure of the strong nuclear force? There is no physical reason. There is no causal connection between the roots of a quintic equation and the behavior of quarks inside a proton. They are completely different domains of reality, and yet the same mathematical object governs both, as if the polynomial and the proton are two manifestations of the same underlying pattern, a pattern that exists independently of polynomials, independently of protons, independently of the humans who discovered either. If that pattern exists independently, then mathematics is not a human invention. It is a feature of reality. It is something the universe is made from, the way a building is made from steel and concrete, except that the mathematical structure is more fundamental than the physical stuff that instantiates it. The groups are more real than the particles. The symmetries are more real than the forces. The architecture is more real than the building. And that is a deeply unsettling conclusion, because it means the work of mathematics is not creation, it is discovery. Galois did not invent groups, he found them. They were there, in the structure of equations, waiting for someone to see them. And they were simultaneously there, in the structure of matter, waiting for physicists to discover them a century later. The same object, in two different domains, found independently by people who had no connection to each other, separated by 130 years, working on completely different problems, as if the architecture kept leaving clues in different rooms for different visitors, knowing that eventually someone would realize the rooms are in the same building. And Galois saw it, not because he was looking for it, he was looking at polynomial equations. Through the equations, he saw the skeleton of a reality that would not be discovered for another 100 years. I keep coming back to the letter. The night of May 29th, 1832. The phrase, "Je n'ai pas le temps," I have not time. Because what haunts me about that sentence is not the tragedy of a young man running out of hours. It is the possibility that the mathematics he was racing to write down was not something he was creating. It was something he was finding, something that had been there, in the structure of numbers and equations, waiting for someone to see it. And the first person who saw it was a political prisoner who had been rejected by every authority in his field, who was about to be killed in a duel he could not refuse, and who had 12 hours to write down as much of the architecture of reality as he could before the sun came up and the pistols were loaded. And the question that sits underneath all of this, the question that nobody in mathematics or physics has answered, is the one Wigner asked. Why does it work? Why does a mathematical structure invented to solve polynomial equations turn out to be the fundamental language of particle physics? Why does the symmetry group of a quintic equation have anything to do with the symmetry group of the strong nuclear force? These are entirely different domains. They have no physical connection. There is no chain of causation linking the roots of a fifth-degree polynomial to the behavior of quarks inside a proton. And yet the same mathematical object, the group, governs both. The same structural logic, the same architecture, as if the algebra and the physics are two windows into the same building, a building that was there before either window was opened. And if that building exists independently of the people who discovered its rooms, then mathematics is not a human invention. It is not a language we created to describe patterns we noticed. It is something else, something that exists whether or not anyone writes it down, something the universe is built from. And Évariste Galois, at the age of 20, did not create group theory. He discovered it. He touched a corner of the scaffold. He saw, through the narrow window of polynomial solvability, a structure that extends in every direction, through geometry, through physics, through the fabric of space-time itself. And he had just enough time to scrawl a fragment of what he saw before the sun came up and the pistol was loaded. He wrote to Chevalier, "After that, there will be, I hope, people who will find it to their advantage to decipher all this mess." It took 14 years for Liouville to decipher the algebra. It took 41 years for Jordan to make it comprehensible. It took 87 years for Noether to connect it to physics. It took 123 years for Yang and Mills to build gauge theory from it. It took 132 years for Gell-Mann to use it to predict a particle, and for Barnes and Samios to find that particle in a bubble chamber on Long Island. 132 years. And every step of that chain confirmed something more unsettling than the last, that the mathematics was not just useful, it was necessary. It was not just predictive, it was constitutive. The symmetry groups do not describe the forces. The symmetry groups are the forces. The representation theory does not classify the particles. The representation theory is what the particles are. The architecture is not a map of reality. The architecture is reality, and the first person to see any of it was a boy who could not get into the École Polytechnique, who was expelled from the École Normale, whose father was driven to suicide by a parish priest, who was rejected by the Academy of Sciences, who spent 6 months in prison for threatening the king, who fell in love with a woman who did not love him back, who was shot in the stomach at dawn, and who died on a hospital floor at the age of 20, having asked his brother not to cry. The manuscripts are at the Institut de France. You can see them if you visit. The handwriting is rushed. The margins are full of crossed-out lines, restarts, and the name Stephanie doodled alongside theorems. There are places where the ink changes shade, where he paused and came back, and in the margins, in the old French spelling that makes the words feel almost desperate, il y a quelque chose à compléter dans cette démonstration. Je n'ai pas le temps. There is something to complete in this proof. I have not time. He did not have time, but the mathematics did. The mathematics waited 14 years for Liouville, 41 years for Jordan, 87 years for Noether, 123 years for Yang and Mills, 132 years for the omega minus baryon to appear in a bubble chamber at 1672 mega-electron volts, confirming that the symmetry structure of a Lie group descended from Galois' concept governs the composition of matter itself. The mathematics waited, as if it knew someone would come, as if the architecture of reality does not care how long it takes for the tenants to learn the floor plan. And the question that will not leave me alone, the one I still do not know how to think about, is not what Galois wrote on the night of May 29, 1832. We know what he wrote. We have read it. We have used it to classify every particle in the universe and predict the existence of particles nobody had ever seen. The question is what he did not have time to finish. What was in the rest of the theory of ambiguity? What the architecture looks like in the rooms he never got to enter? What is written on the pages that do not exist? Because a boy ran out of hours, and a pistol was loaded at dawn, and the greatest mathematical mind of the 19th century bled out on a field in the 13th arrondissement of Paris. I keep thinking about the theory of ambiguity, those last 2.5 pages, the ones that anticipated Riemann surfaces and monodromy and Grothendieck's algebraic geometry. Galois was 20 years old. He was writing mathematics that the mathematical community would not begin to comprehend for over a century. And in the margins he wrote, "There is something to complete in this proof. I have not time." Here is what we know about the theory of ambiguity from the fragments that survive. Galois was trying to extend his symmetry methods from algebraic equations to what he called transcendental functions, functions defined by integrals rather than by polynomial expressions. He was looking at integrals of algebraic functions, the kind of thing that arises when you try to compute the arc length of an ellipse or the period of a pendulum. These integrals have a peculiar property. If you move around a singular point in the complex plane, the value of the integral changes. It picks up an additional contribution, and the set of all possible contributions you can pick up by moving around all the singular points forms a group of symmetries of the integral. This is what is now called the monodromy group. Galois was seeing this in 1832. Riemann would not publish his work on what we now call Riemann surfaces until 1851. 19 years later, the systematic theory of monodromy would not be developed until the 1870s and 80s. And the deepest engagement with the structures Galois was gesturing toward, the Galois theory of differential equations, the algebraic fundamental group, the connections between number theory and geometry, through shared symmetry structures. These are research programs that were not fully articulated until the work of Grothendieck in the 1960s and beyond. Grothendieck. Alexander Grothendieck, born in Berlin in 1928, raised in occupied France, stateless for most of his early career. He revolutionized algebraic geometry in the 1950s and 60s by recasting the entire subject in terms of category theory and schemes, creating a framework of almost terrifying generality. And at the heart of his vision was something he called the Galois theory of schemes, an extension of Galois' original correspondence between field extensions and groups to the setting of algebraic geometry. The fundamental group of Grothendieck's theory, the étale fundamental group, is a direct generalization of Galois groups. Grothendieck knew he was extending Galois. He said so explicitly. And here is the thing that keeps me awake. Galois' theory of ambiguity, those 2.5 pages from May 29th, 1832, gestures toward exactly this territory, toward the connection between algebra and geometry through shared group theoretic structures, toward the idea that the symmetries of a polynomial equation and the symmetries of a geometric space are manifestations of the same underlying concept. Grothendieck arrived at this connection through decades of systematic development, building an enormous theoretical apparatus to reach the insight. Galois appears to have glimpsed it directly, in a single night, at the age of 20, without the apparatus, as if he could see the destination without needing the road. What else could he see? What was in the rooms he did not have time to enter? We will never know. And the not knowing is not just a biographical regret. It is a mathematical loss, a loss that has weight and consequence. Because if Galois could see the connection between algebra and geometry in 1832. And if it took the mathematical community another 130 years to reconstruct what he saw, then the question of what else was in his head, the things he could not even sketch in those 7 pages, is not idle speculation. It is a question about mathematics that remains undiscovered, about rooms in the architecture that nobody has found yet, about pages that were never written and that might have changed the shape of human knowledge. What if he had time? It is a question that cannot be answered, and I know that, and asking it anyway is the kind of thing that keeps me awake. Because think about the rate at which Galois was producing foundational mathematics. Between the ages of 17 and 20, a span of roughly 3 years, he invented group theory, created the entire framework of abstract algebra, solved the problem of polynomial solvability that had been open for 3 centuries, discovered finite fields, found the exceptional isomorphisms in the modular group, and sketched applications to transcendental analysis that would not be understood until the late 20th century. 3 years. If you extrapolate that rate of discovery over even another decade, which is conservative for a mathematician who typically hits peak productivity in their 30s, the amount of mathematics that was lost is beyond estimation. Abel's story makes this concrete in a way that I find almost unbearable. Abel died at 26, 3 years older than Galois. In those extra 3 years, Abel had expanded his impossibility proof into a comprehensive theory, developed the theory of elliptic functions to a level that Jacobi and Legendre recognized as epochal, and laid groundwork for what would become algebraic geometry. 3 years produced a body of work that won him a posthumous grand prize and eventually got a major mathematical prize named after him. The Abel Prize, the mathematical equivalent of the Nobel, was established in 2002 by the Norwegian government, 173 years after Abel's death. Galois had those same 3 years. What he might have done with 3 more, or 10 more, or 30 more is a void in the history of mathematics that can never be filled. And the void is not abstract, it is specific. There are theorems that were not proved, results that were not discovered, connections that were not made, problems that took decades longer to solve because the person who would have solved them was lying in an unmarked grave, and the institutions that created that void were never held accountable. Cauchy, who sent the manuscript down a path that ended at a dead man's desk, continued his distinguished career. Poisson, who rejected the work as insufficiently clear, remained a respected member of the Academy. Liouville, who sat on the papers for 3 years after recognizing their importance, is remembered as the man who rescued Galois, not the man who delayed him. The École Polytechnique, which rejected Galois twice, continued to train mathematicians for decades who would have been humbled by his work. The cost was externalized. It was paid by mathematics, by physics, by every discipline that would eventually depend on the framework Galois created. It was paid by every physicist who spent years developing results that group theory would have handed them. It was paid by every graduate student who struggled with problems that Galois' completed theory of ambiguity might have illuminated. It was paid by knowledge itself, and the pattern continued after Galois. Emmy Noether, barred from presenting her own theorem because she was a woman. Yang and Mills, challenged by Pauli at their seminar and left without an answer for a decade. Galois, Abel, Noether, outsiders rejected by the institutions that should have embraced them, vindicated decades after the work was done, honored posthumously or belatedly by the same establishments that had blocked them. The pattern does not change. The mechanism is not conspiracy. It is something worse. It is the ordinary, day-to-day operation of institutions that are designed to maintain consensus, and that therefore systematically fail to recognize the people who see past the consensus. Think about how the Academy treated Abel. He sent his impossibility proof to Cauchy. Cauchy did not read it. He sent a major memoir on elliptic functions to the Academy during his visit to Paris in 1826. Cauchy was appointed referee and mislaid the manuscript. Legendre, when he finally saw it, called it a mess. Abel returned to Norway penniless, sick with tuberculosis, and died 2 days before a letter offering him a Berlin professorship arrived at Froland. Krell had been trying to secure the position for years. It came 2 days too late. And how the Academy treated Galois. Cauchy redirected the manuscript. Fourier died with it on his desk. Poisson rejected it. Louville recognized it, but delayed publication for 3 years. Jacobi and Gauss, the 2 greatest living mathematicians, were publicly asked to give their opinion, and never responded. Not a word. Not a single word from either of them about the work of a 20-year-old whose dying wish was that they read it. 2 young men working on the same class of problems, both submitting to the same institution, both ignored, lost, rejected, both dead before 30, both vindicated posthumously, both eventually honored with their names on foundational theorems and prestigious prizes, the Abel Prize, the Galois theory. Their names are everywhere now, in textbooks, on university buildings, in the citations of Nobel Prize-winning work, but the names are memorials, not rewards. The rewards went to the institutions that survived them. First it was impossible. Then, when someone did it, it was trivial. The one thing it could never be was important. Galois' brother Alfred spent his entire life arguing that the duel was a political assassination. He believed that agents of the government had arranged for Évariste to be killed. The evidence for this is thin, as Rothman's scholarship has shown, but I understand the impulse, because even if the pistol was not held by a government agent, the system that produced Galois' death was political. It was political in the broadest sense. A boy genius was expelled from school for his beliefs, imprisoned for his speech, rejected by the Academy for writing mathematics that challenged the conceptual limits of his referees, and then killed in a duel that was the direct product of the volatile social world he had been pushed into by every institutional door that closed in his face. Nobody ordered Galois' death, but the institutions that surrounded him created the conditions for it with a consistency that looks, in retrospect, almost like intention. And the mathematics he carried was lost with him. Not all of it. The premier memoir survived. The testamentary letter survived. Enough survived to build group theory and reshape all of algebra and eventually provide the language for all of physics. But the theory of ambiguity did not survive in completed form. The applications to transcendental analysis did not survive. Whatever else was in his head, the connections he had not yet written down, the theorems he had not yet proved, the rooms of the architecture he had glimpsed but not entered, all of that died on May 31st, 1832, and we will not get it back. That is the part that does not resolve. The vindication of Galois is real. His work has been published. His name is on the theory. Every algebra textbook in the world teaches Galois theory. Every physics department in the world uses group theory. The omega minus was found. The standard model was built. The Higgs was discovered. The architecture he saw is now the foundation of our understanding of the universe. But the architecture is incomplete, and the person who saw further into it than anyone else alive is buried in a grave nobody can find. Nobody knows. And we will not know, because Évariste Galois lies in an unmarked common grave at Montparnasse, and the unfinished proofs were never written, and the mathematics that would have been on them is still out there, somewhere in the structure of things, patient and exact, and invisible, waiting for someone to see it, the same way it waited the last time.